Hello Pre-Calc BC. Today is the day you've been waiting for. We're going to talk all about horizontal and vertical asymptotes. And spoiler alert, there's another type of asymptote that your teachers held out on you last year. So you're going to learn all about something else called an end behavior asymptote today. Get excited. All right, so we are going to start with this function right here, r of x equals, and then you can read the rest. And what we're going to do is we are going to simplify this first, and then we will look at all of this information I have written down for you. Okay, so first we're going to simplify. Let's take out a 3 up top, and then that can factor some more, right? It's going to be an x plus 5, x minus 2. So there we go. That's looking good. I'll get rid of this for now. And then in the denominator, I can take out a 4. And I can factor that further, x plus 2, x minus 2. And now we have these x minus 2's. They're going to cancel. And we can rewrite our simplified function. Okay. All right, so now that we actually have simplified a function, let's take a look at these different attributes of it. All right, so vertical asymptotes. To find a vertical asymptote, if possible, we're going to factor and reduce the function. Okay, we did that. You're going to set your denominator equal to 0 and then solve. Okay, cool. So here's our denominator. We're going to set it equal to 0 and solve, and then write the equations of any vertical asymptotes. Okay, so let's do that down here. And actually, let's rewrite our r of x as well. It was 3 over 4, x plus 5, x plus 2. So vertical asymptote, set your denominator equal to 0, and then make sure that you actually put your x equals. Okay, vertical asymptote, check. Holes, removable discontinuity. Removable discontinuity is a calculus term. We'll use that a lot more second semester. You're going to go back to your factored function. Any factor that cancels out yields a hole. So that would be this x minus 2 right here. We're going to set that factor equal to 0 to solve, to find the x coordinate of the hole. Substitute that x value into the reduced function to find the y coordinate of the hole. All right, so x minus 2 equals 0, x equals 2. What that is telling you is that the x coordinate of your hole is a 2. To find the y coordinate, you must plug this 2 into the simplified function. Because guys, look, what happens if you plug the 2 into the original function? You're going to get a 0 in your denominator. You're not going to be able to do anything. It has to go into the simplified one. So this would be 2 plus 5 is 7, and 2 plus 2 is 4, and 3 times 7 is 21 over 16, which I don't think simplifies. Okay, there, we have found the hole. End behavior asymptote. Now, last year you were just told about horizontal asymptotes. So a horizontal asymptote is actually a subset of something called an end behavior asymptote. And really what an end behavior asymptote does is it tells you what your end behavior is. Okay, it's an asymptote that determines what your end behavior is. So a horizontal asymptote is one of those things. There's also called an oblique asymptote, which is an asymptote that is a line. But not all asymptotes are lines. Okay, which, all right. So here's what you knew from last year. When you have a horizontal asymptote, if the degree is bigger in the denominator than the degree in the numerator, we say our horizontal asymptote is y equals 0. All right, so for example, if you had a y equals 2x over x squared, okay, the degree is bigger in the denominator, so we say the horizontal asymptote is y equals 0. This is also the reason why our reciprocal function, y equals 1 over x, has a horizontal asymptote of y equals 0, because the degree is bigger in the bottom. All right. Option 2, if the degree in the numerator and the denominator is the same, the horizontal asymptote is the ratio of the lead coefficients. So that's weird. Both of these are x squareds on the top and the bottom. So what we do is we take the ratio of our lead coefficients. That was supposed to be highlighter. I'm not actually crossing it out. And your horizontal asymptote would be y equals 2/4 or 1/2. Okay? Now, here's where you weren't lied to. It's just you didn't get the whole truth last year. What you were told last year was, if the degree in the numerator is bigger than the degree in the denominator, there's no horizontal asymptote. That is true. That would be like if you had a y equals 5x cubed over x. You said, oh, the degree's bigger in the numerator, no horizontal asymptote. And then you, done. Okay, well that time has passed. We're not done anymore. There isn't a horizontal asymptote. There is some other type of end behavior asymptote. So what I'm going to do today is show you how to find that. If there is no other horizontal, or if there is no horizontal asymptote, there is another type of end behavior asymptote. Okay? It always has some form of end behavior asymptote, even if it's not horizontal. What we're going to use is long division to find that end behavior asymptote. Okay, so remember last year you learned synthetic division, which we'll look at again, and then you spent like a day on long division, and then you like never did anything with it ever again. Okay, long division is back, people. You need to know how to do long division. If your end behavior asymptote, your EBA, is a linear equation, it is called an oblique asymptote. Why, I'm not really sure. And that's just some vocabulary that your book uses, so you're aware. All right, so here we go. Let's try it. Oh, I guess we should actually find the EBA for this problem, huh? So in this situation, you do have the same degree, right? It's an x over an x. So it's just the ratio of the lead coefficients, and we do have a horizontal asymptote of y equals 3/4. Okay, now to be clear, a horizontal asymptote is an end behavior asymptote. So I can still call that an end behavior asymptote. It just happens to be horizontal. Okay, next, we are going to factor completely, and we are going to find all of this given information. Now, these next two problems are pretty intense to factor, but I do think it's important that you get some practice in this. Most of the time, it will not be as time-consuming to factor these. What I would say about the numerator of this first problem is that we can take out just a -2 from everything. So I'm just going to do that first. So x cubed plus 4x squared minus 9x minus 36. All right, and then when you have a group of 4 like this, or a polynomial with 4 terms, it is a good idea to see if you can factor by grouping. So let me remind you of how that works. You're basically going to factor out the GCF from the first 2 terms and from the last 2 terms. So I'm going to keep this -2. And these first 2 terms, I can take out an x squared, and I'd have an x plus 4 left. And then the second 2 terms, I can take out a -9, and lo and behold, I have an x plus 4 left. So now I can factor by grouping. This becomes x squared minus 9, and the x plus 4. Okay, and then finally you have difference of squares. So we have this, and this is just the top of this whole thing. Okay, and so the bottom though, the bottom is just going to be an x plus 5, x plus 4. All right, so let's rewrite a of x. 2, x plus 3, x minus 3, x plus 4, all over x plus 5, x plus 4. Okay, and we should notice that our x plus 4s are going to cancel. So we'll rewrite our final simplified form. If you're like, oh my god, normally it won't take this long. All right, so let's make sure I have the same thing that's on my paper. Yes, that looks good. The bad thing about recording these videos is that when I make little mistakes, usually in class, someone will be like, yeah, you messed up. But with this, it's just me. There's no one to correct me except for me. So I just want to reference my notes and make sure that I actually have what I should have. Okay, so now let's just start finding some of this stuff. Vertical asymptotes are super easy to find. Just look at your denominator. We have an x plus 5 left. All right, vertical asymptote is x equals -5. Okay, horizontal asymptote is going to happen when our degree is bigger on the bottom or our degrees are equal. Is that happening here? No, of course not, because I have to show you this new thing that you haven't learned yet. So you're just going to say none. There's no horizontal asymptote. There's going to be another end behavior asymptote. All right, but to be clear, a horizontal asymptote is a type of end behavior asymptote. Holes. Our x plus 4 is canceled, so we're going to have a x coordinate of -4 for the hole. I'm going to actually move that down here. Okay, and then to find the y coordinate, we are just plugging that -4 in to this simplified function. So here we go. -4 plus 3 is -1. -4 minus 3 is -7. -4 plus 5 is 1. So I have -2 times -1 times -7, which should be a -14. And that's the whole. Okay, so now this end behavior asymptote. Okay, we have determined the degree is bigger on top. That means we are going to need to do long division. So you're going to use the original function, not the factored form. We have -2x cubed minus 8x squared plus 18x plus 72. It is getting divided by x squared plus 9x plus 20. So yeah, so you are going to write it like this. Okay, let's do some stretches. Oh, okay, you ready? Here we go. All right, so here's what you're going to do. You're going to say x squared times something is -2x cubed. And that would be a -2x. And so what I like to do is I'm going to put this -2x right here. I'm putting it over the other x. That also is going to tell me how many cycles of this I have to do, which you'll see what I mean by that in a minute. All right, now we multiply. -2x times x squared is -2x cubed. -2x times 9x is -18x. -2x times 20 is -40x. Okay, and then in long division we are subtracting. -2 minus -2 cancels. -8 minus -18, that's -8 plus 18, that's 10, and I lost my squared right here, 10x squared. 18 minus -40, that's 18 plus 40, which is 58x. Okay, bring down your 72. Okay, now we're going to do this again. X squared times something is 10x squared. It's a positive 10. Multiply. 10 times x squared. 10x squared. 10 times 9x. 90x. 10 times 20. 200. You are subtracting. 10x squared minus 10x squared cancels. 58x minus 90x is -32x. And 72 minus 200 is -128. Okay, so now here's the good news. See how you've run out of spaces up here? Okay, that's because x squared will not go into -32x. Your degree up here is now bigger than your degree down here. So essentially what this means is this is your remainder, but the remainder does not matter. Okay, The remainder does not matter. This is what matters. This is your end behavior asymptote. All right, so that's super abstract. You're probably like, okay, cool, I did long division, but like what does any of this mean? So I'm going to pause my video, give me 1 second. I'm going to get this typed into my calculator and I'm going to show you. BRB. All right, I'm back. So I typed my rational function into my calculator and I typed in the simplified version, but you could also type in the original. To be perfectly honest, I just type in the one that looks like it's going to be faster to graph. So if you press graph, okay, here's what this looks like. Now, rule of thumb here, this is important. We had a vertical asymptote somewhere. Where was it? At -5. Because of the idea of intermediate behavior, vertical asymptotes always have something on the left and the right of it. So if you look, here's my vertical asymptote. That means there's got to be something else on the other side of this line. So I'm going to move my window up. I don't actually know how far up I have to move it. Oh, there it is. Okay, so it's right there. So now you see your vertical asymptote. Where's this end behavior asymptote come into play? Well, let me show you. It was y equals -2x plus 10. So now I'm going to type that in. Okay, so check this out. That red line is the end behavior asymptote. I want you to notice how this blue right here and this blue right here, it's approaching that red line. That's because that red line, our asymptote, is affecting what the graph is doing. Isn't that so cool? This is always a lesson I really love teaching in class, so I'm sad that I can't see you get as excited as I am. All right, so now we have one more of these. I do think it's important that you go through the whole thing, but this would be a good one for you to pause and try to do as much as you can and then check back in with the video. Okay, so, but I'm just going to keep on teaching. All right, factor. Well, this top, I can definitely take out an x, right? So I guess I'll do that. X to the 4th minus 5x squared plus 4. And then this is a type of factoring we haven't talked about yet. This is just like regular factoring. I mean, you learned it last year, but we haven't talked about it. It's just regular factoring, but instead of x's, we have x squareds, and we're multiplying to 4, and we're adding to -5, and that's going to be a -4 and a -1. And then, lucky us, we get to do some more difference of squares. Okay. So that's the top. Let's just leave that alone for now. And then the bottom, what I'm going to try to do is that factor by grouping again. And usually if there are 4 terms, it's a good guess. You can't always factor by grouping, but a lot of times you can. So I'm going to take out an x squared. That's x minus 2. And then I'm going to take out a -9. It's x minus 2, and since these x minus 2's are the same, I can factor it by grouping. X squared minus 9, x minus 2. Now, if those x minus 2's are not the same, then you are out of luck. It is not going to factor. And then you'd probably have to graph it to find your intercepts. Okay, so now, what was this, b of x? Let's write the whole thing. X plus 2, x minus 2, x plus 1, x minus 1. Maybe if I use weird voices, you'll be more entertained by this. X plus 3, x minus 3, x minus 2. The only thing that's going to cancel are my x minus 2's, hopefully. Yes, good. All right, final factored form. X plus 2, x plus 1, x minus 1, x plus 3, x minus 3. Oh, that was thrilling. Okay, vertical asymptotes. Those are related to these guys. Okay, so we should have vertical asymptotes at x equals -3 and x equals +3. Horizontal asymptote. Well, sad day for us. The degree is bigger in the top, so there is none. There's going to be instead another type of behavior asymptote. Holes. We did have this x minus 2 cancel, so that means I have an x coordinate of 2 for my hole, and now I'm going to plug it in. 2, 4, 3, 1, 5, -1. All right, let's see. 2 times 4 is 8, 2 times 3 is 24. 24 over -5 is what I'm getting. Okay, and then finally our behavior asymptote. So let's go ahead and divide this. And the one on top, the bigger degree, we put that underneath. And then this is important, something to look out for. You're missing an x to the 4th here and an x squared. So you're going to need to put a placeholder of those in here. Plus 4x. And then I'm going to put a placeholder at the end as well, since we don't have a constant. X cubed minus 2x squared minus 9x plus 18. Okay, and here we go. We say x cubed times something is x to the 5th, and that's just x squared, and I'm going to put it right here because it lines up over the x squared, and this tells me I'm going to have 1, 2, 3 cycles of this because there are 3 spaces left. Okay, multiply x to the 5th, -2x to the 4th, -9x cubed, 18x squared, and subtract. Cancel. 0 minus -2, +2, -5 plus 9, 4x cubed, 0 minus 18 is -18x squared. Bring down your 4x. Whew, I gotta stretch again. Okay, I just heard something pop. That was bad. Okay, now we try it again. X cubed times something is 2x to the 4th. That's 2x. And now we multiply again. 2x times x cubed, 2x to the 4th. 2x times -2x squared, -4x cubed, 2x times -9x, -18x squared, 2x times 18, 36x, and subtract. Okay, 2 minus 2 cancels. 4 minus -4 is 8x cubed. -18 plus 18 cancels. 4 minus 36 is -32x. And actually, you know what? You'll see why, but bring down your 0x squared, and then you can bring down your plus 0 as well. And I'm jumping back in my video, so excuse that. All right, last time through. X cubed times something is 8x cubed, 8. And then we multiply 8 times x cubed, 8x cubed. 8 times -2x squared, -16x squared. 8 times -9, -72x. 8 times 18, 144. And you are subtracting. And what's going to happen is you're going to get a 16x squared, and you could keep doing more, but look, your degree is now bigger, and so you're done. So our asymptote is y equals x squared plus 2x plus 8. And this one looks so cool. So give me just a minute to type it into my calculator. All right, I typed this in, and it looks like this. And remember what I told you is that when you have vertical asymptotes, and we had 2 here, that you always have something on the left and the right. So our vertical asymptotes are here, which means there is something more going on. And you know it's going to be up as opposed to down, because if you look, your degree of your vertical asymptotes were 1s. So since here we're going down, that means on the other side of the vertical asymptote, they have to be going up because of what we learned about intermediate behavior and the degree of the vertical asymptote. So that means I'm going to move my window way up again. I'm going to try 100. There it is. Okay, so it's a lot more than what you can just see. And let me move my Y min. I'm just going to make it look a little more even. Okay, so here are my vertical asymptotes, all right? And now I'm going to put in the end behavior asymptote, which was x squared plus 2x plus 8, I want to say. So again, what this should be doing is it's influencing the curve. It's showing where the end behavior ends up. And check this out. Look at that, okay? That red parabola, our asymptote, is telling our blue curve what to do as x approaches infinity and as x approaches negative infinity. Now, one more thing I want to mention briefly, and we're going to talk more about this tomorrow, is way back when, couple lessons ago, I talked about how the x-intercepts of the graph can be found in the numerator. Okay, I think that was back on day 2 maybe. Okay, so if you look at our numerator, this is actually going to tell you all of your x-intercepts. We're going to have an x-intercept at x equals 0, at x equals -2, at x equals -1, and at x equals 1. And sure enough, if you go, I know right there it doesn't really look like a whole lot, but if you go to your table and you look at 0, 0, 0, 1, 0, what were the other ones I said? -1 and -2. Oh, there it is, -1, 0, and -2, 0. So those are all of your x-intercepts. You can see that in the numerator of your equation. Okay, we'll talk more about that tomorrow. Have a great day.